Now we want to look at a new topic. We want to be able to understand weathering and soils. All right. We want to be able to understand weathering and soils. What is weathering? What is weathering? So weathering is the breakdown of rocks, soils, and minerals to form new minerals that are stable on the surface of the earth. So weathering, as we know from the primary definition, rocks are breaking down to form soils and minerals. All right. So rocks are breaking down and it's going to form a soil. All right. So when we have rocks breaking down, or the breaking down of rocks, or even a soil and a mineral, even a mineral can also break down to form another mineral. All right. We know some minerals are more stable than other minerals. Is that not it? Some minerals are more stable than other minerals. All right. So through contact with the Earth's atmosphere, all right, biota or biosphere, and then the hydrosphere or the waters. Weathering essentially occurs in situ. Weathering occurs in situ, meaning we don't have any movement when we use the term weathering. Whilst erosion involves the movement of rocks and minerals by agents such as water, ice, snow, wind, waves, and gravity. It means the action or the act, all right, the action by which we have the breakdown of the rock is weathering. When we mention erosion, it means it involves transport. There must be movements of the broken down or weathered materials. So the transport of these broken down materials, rocks and minerals by agents such as water, ice, snow, wind, waves, and gravity is what we term erosion. We can basically classify erosion into two broad categories. Physical weathering and chemical weathering. All right. So in some texts, you may hear of biological weathering as well. All right. But in here, we have two major groups: physical weathering and chemical weathering. All right. Physical weathering and chemical weathering. What is physical weathering? It involves the breaking down, it's just the mechanical breakdown of large rocks into smaller ones. It involves a physical or mechanical process. It is just a disintegration of the rocks. So the key word here is disintegration, all right? Not decomposition, disintegration of the rocks and minerals by a physical or mechanical process. Examples of this as frost wedging. We do know that especially in the temperate zones, when water enters cracks or joints in rock masses, it could freeze. When it freezes, we know that when water freezes, the volume increases. And this can exert pressure on the walls of the rock and cause this breaking down. Is that not it? Breaking down because it's expanding. Then we could also, in our part of the world, instead of frost wedging, we are likely going to have thermal expansion and contraction. So in the tropics, we have very hot days and then cool weather. So when we have heating and cooling, this cycle, it's heat expansion and contraction. So thermal expansion and contraction. When this continues day after day, month after month, and then year after year, we are going to have weathering or breakdown. Then we could also look at abrasion. So we do know that when we see rocks in the stream channel, the pebbles that we find around it, right? Because the rocks are, as the stream is carrying them, they are colliding with each other and getting rounded. That's abrasion, is weathering. That is why on the riverbeds, we have a lot of sand. they are products of the weathering, right? Then we have organic activity. So roots of trees we know may try to force their ways through these cracks and crevices and may push through the rocks and cause weathering. Also, we could have crystallization. When we have crystal growth, it could exert some stresses, all right, because as this particular change in physical states of an element or compound occurs, as the temperature variations occur, we could have crystallization, and this can also result in weathering. So in summary, as far as physical weathering is concerned, we could have thermal expansion and contraction, we could have frost wedging, abrasion, organic activities, and crystallization. All right. So like we already mentioned, in physical weathering, the breakdown of rocks and soils are through direct contact with the atmosphere, such as heat, water, ice, and pressure. In chemical weathering, it's involving the direct effects of atmospheric chemicals or biologically produced chemicals. All right. So here we are dealing with some chemicals, either from the atmosphere or from biological organisms. All right. And these both processes work together to break down rocks and minerals to smaller fragments. As far as physical weathering is concerned, we do know that we have development of joints, right? So joints are nothing but fractures in the rocks, the cracks that we find in the rocks. And then this could be regularly spaced generally. And joints may develop as a result of expansion. So we call them, you could have cooling and shrinkage joints. Is that not it? As a result of expansion, we could have development of joints. And then these joints form free space in the rocks. And these free spaces form the points of contact through which various agents of physical or chemical weathering can now enter and cause further breakdown or further weathering. So here we see these rock masses and we see them broken down. All right, so these are various joints networks. So in chemical weathering, what's happening? We have a change in the composition of the rocks, often transferring them into when water interacts with the minerals to create various chemical reactions. Chemical weathering is a gradual and ongoing process because the mineralogy of the rock continues to adjust to the near surface environment. In physical weathering, no new minerals are formed, but in chemical weathering, new minerals may be formed. So new minerals or secondary minerals develop from the original minerals. But we don't see that in physical weathering. All right. We don't see that in physical weathering. So as far as chemical weathering is concerned, we know that we have differing conditions. And due to these differing conditions or variations in conditions, minerals in rocks can react with their new environments. And this will result in the production of new minerals that are much more stable under the specific temperature and pressure conditions on the surface. So minerals that are much more stable under pressure, temperature, water, and oxygen conditions near the surface, we can put this in the order of the most stable to the least stable. So we can have iron oxides, aluminum oxides, such as hematite, all right, Fe2O3, and then gibbsite, aluminum hydroxide. Quartz, we do know quartz is very stable, right? And that is why we even use quartz for construction. So even sand is more like silica sand, right? Quartz, SiO2. Then clay minerals, muscovites, alkali feldspars, biotites, amphiboles, pyroxenes. Then we have the calcium-rich plagioclase and then olivine. All right, so it means that is the decreasing order of stability. And later on, we'll find out that at the same time, this particular minerals that are least stable, that are not stable, were formed at very high temperatures. So under the current temperatures, they can no longer be stable. So they'll have to break down and form new minerals that will be stable under the current pressure, temperature, water, or oxygen conditions near the surface. All right. This brings us to the concept of Bowen's reaction. So Bowen's reaction theories. So basically, Bowen's reaction states that we have different environments of formation. And then due to the environments of formation, from a melt or magma, we are going to have certain magmatic differentiation. In other words, we are going to have certain crystals forming first before other crystals. So it's like traveling to a destination. So when we get maybe to the first town, that is somebody's destination. So the person is going to get down. The bus does not stop. That's not the final destination. So the bus will continue to move. When we get to another town, those who have reached their destinations will get off the bus. The others continue until the final destination. So more or less, that is the concept of the Bowen's reaction series. So the first elements to crystallize do so under very high temperature conditions. All right. And we are likely going to have olivine coming out of the melt first, then pyroxene, then amphiboles, then biotites. All right. So in that kind of order. Then to the right, so we have the continuous series and the discontinuous series, something like that. I think we'll mix this again later. We have the calcium feldspar, and then all the way to the sodium feldspar. So for those of you with backgrounds in geology, you remember that the calcium feldspar, we also refer to the calcium feldspars. We have this plagioclase series, right? Plagioclase series. So sodium feldspars, that is albite to calcium feldspar, also called anorthite at the extreme end. So anorthite to albite. All right, anorthite to albite. All right, so we are basically trying to say that at the highest temperatures, some minerals will form first. Then as the temperature reduces, other minerals are forming until the temperature of the melt reduces completely. And the rest of the magma is now going to be very rich in quartz or silica, SiO2. All right, principally the material that sand is composed of. And so you see the temperature is approaching near surface conditions, right? Lower temperatures by the time quartz is forming. So this will be most resistant. And the least resistance will be the ones that were formed first. All right, the ones that were formed first. So this is the decreasing order. All right, decreasing order of how do you call it? Resistance, and this will be increasing order of resistance. So from olivine to quartz, the order of resistance is increasing. So quartz is very, very stable, very, very stable. That's why we find a lot of quartz available. All right. So what are the agents of chemical weathering? The first agent we want to look at is water and weak acids formed in water. Water and weak acids formed in water. So an acid is a solution, we already know, that has abundant free hydrogen ions, right? Then we know that the most common weak acid that occurs in surface waters is carbonic acid. Carbonic acid. I'm sure we might have heard about acid rain, acid rain. How does carbonic acid form? So we have water. Water combines with carbon dioxide. When that happens, we are going to form a weak acid called carbonic acid. All right, carbonic acid. And this could further break down to release the hydrogen ion and then bicarbonate ion. Bicarbonate ion. All right. So this hydrogen ion, the small ion, but then it can easily enter the crystal structures, releasing other ions into the water. And this can cause breakdown. Another type of chemical weathering is hydrolysis. Hydrolysis. So in the first one, we said water and weak acids formed in water. So principally, we know water can combine with carbon dioxide, and this can form carbonic acid. Now, hydrolysis is a chemical weathering process, and it affects silicates and carbonate minerals. All right. So, for instance, we could have olivine. All right, olivine plus carbon dioxide. So olivine is rich in magnesium, so it's magnesium silicate plus carbon dioxide, and then in the contact with water. So this chemical reaction is going to release magnesium, and then we are going to have what? Carbonates, is that not it? And then we are going to have some what? Silicates. All right. Now, this reaction is much more common. So this particular reaction is much more common and an important reaction in controlling the amount of carbon dioxide in the atmosphere. So when we find this kind of bicarbonate ions plus this, how do you call it, silicic acid, because of the hydrogens, we know this is an acid, right? Silicic acid in solution, this can cause dissolution, or in other words, can cause the chemical breakdown of this particular rocks. And this process is hydrolysis. All right, hydrolysis. So it's an ionization of water, ionization. So it involves silicates and carbonate minerals. So olivine, for instance, and then carbon dioxide kind of coming together because carbon dioxide and water are already present in the environment, right? And then when they come into contact with, say, olivine, this particular reaction could take place, releasing magnesium, bicarbonate ions, and then silicic acid in solution. All right, silicic acid in solution. All right. So here we see that this particular phenomenon is controlling carbon dioxide because in the reaction, carbon dioxide is sort of eliminated, right? We could also have leaching. So we do know leaching is employed in the mines, right, to remove gold. So what is leaching? It's a process by which ions are removed by dissolution into water. So in leaching, ions are removed by dissolution into water. So if you pour a particular chemical solution on a rock, it could go through and dissolve. Say we are looking for gold, so we pour whatever leachate we are looking for, or whatever material we are looking for, the chemical, all right, say cyanide, it will go through, and since it's the solvents, it can dissolve gold, it will dissolve the gold, we can collect that solution, and then we can now try to recover our mineral of interest. So here, for instance, we find autoclase. It's a mineral, all right, it's a feldspar. Potassium feldspar is a mineral, all right, autoclase. Autoclase is a mineral. It's a feldspar. So we have the feldspars, autoclase, and then we have the plagioclase feldspars, the calcium and the sodium I mentioned earlier. All right. So you should just know that this is a type of a mineral. All right. Then we have hydrogen ion, and then we have water. In this reaction, we are going to release a lot of potassium ion. Then we are going to release kaolinite, which is a clay mineral, kaolinite. And then a lot of quartz, right? Quartz, silica. And we do know silica is stable, right? So we are getting into more stable forms, kaolinite. So that's the process of leaching. So ions are being removed. So here the potassium is literally isolated, right? It's removed. Ions are being removed by dissolution into water. And this can cause the breakdown of the rock. It's chemical. Then we could have oxidation. So in oxidation, what is happening? We have free oxygen, right? So this free oxygen is going to react with minerals to change the oxidation state of the ion. All right. So we do know from the basics that oxidation state is just the charge that the ion carries. So for instance, let's take oxidation of Fe2 plus ion and combination with oxygen and water to form Fe3 plus hydroxide. All right, so we see that the oxidation state of the first ion is what? 2 plus or plus 2, and the second ion is plus 3. We do know ion can exist with different charges. 1, 2, 3, plus 1, plus 2, plus 3. All right, from basic chemistry. So here we have ion, charge of plus 2, combining with what? Silicate, right? So what we have there is pyroxene. Pyroxene. All right. So you remembered we met pyroxene from Bowen's reaction. We saw olivine, pyroxene. So this particular mineral, pyroxene. All right, pyroxene. All right, pyroxene. So we met olivine also, which is magnesium silicate, and then pyroxene, which is iron silicate. Mixing or combining, reacting with oxygen, we are going to change to form magnetite, right? Magnetites and then quartz. Magnetites and quartz. All right, magnetites and quartz. So this is an oxidation reaction. So free oxygen is reacting with minerals to change the oxidation state of an ion. All right, free oxygen is reacting with minerals to change the oxidation state of an ion. So here, due to the oxidation, the original ion 2 plus combines with oxygen and it forms ion 3 plus, and then ion 3 plus hydroxides, and then also maybe some oxides, all right, such as goethite, limonite, and hematite. All right. We could also have dehydration. In dehydration, what is happening is that we are removing water. Is that not it? If I say I'm dehydrated, it means I'm thirsty. I've lost a lot of water. So in dehydration, we have removal of water or hydroxide ion from a mineral. All right, so here we see that we have this ion, hydroxide, right? So we have goethite. Due to the removal of the OH group, it forms hematite and water. So that is dehydration. So removal of water is dehydration. Then we could have complete dissolution, like everything is just dissolved. All right, like calcites. These are very weak when they come into contact with water, especially weak carbonic acids. We already mentioned carbonic acids, right? Where we have water combining with carbon dioxide to form a carbonic acid. So when calcium carbonate, Caco3, calcite, limestone, reacts with carbonic acid, it's going to form calcium ion and then bicarbonate ion. All right, then we can talk about carbonation, that is rocks which contain calcium carbonate. So basically, these are the processes: dissolution, dehydration, oxidation, and leaching. We can also mention hydrolysis, then water and weak acids form in water. These are all agents or different types of chemical weathering reaction. So with respect to the stabilities we talked about, so we can remember that We have the rock like granite. All right, I showed you a picture of granite much earlier on. It has big crystals in it. So granite is coarse-grained. It's an intrusive igneous rock. So even if you see a granite on the surface, it is because it became exposed due to erosion and uplift over the years. So it's coarse-grained, meaning it's the magma cooled below the surface. So it's an intrusive, all right, intrusive or plutonic rock. The primary minerals it contains are feldspar, micas, quartz, iron, and magnesium. So when we have weathering, it will produce clay minerals. All right. Micas will also produce clay minerals. Quartz will form quartz because it is a very stable mineral. So iron, ferromagnesium minerals, iron and magnesium will also form some clay minerals and other iron hydroxides like hematite and goethite. And the leach ions could be plus magnesium. All right, magnesium. Similarly, with basalt, it could break down to form different primary minerals, breaking down to form residual minerals. All right. So this is exactly how these particular minerals, which may not be stable, but then when they break down, they'll form a new mineral that will have a better degree of stability. All right. So we have different types of weathering rinse and exfoliation. Exfoliation or weathering rinse. So this weathering rinse, you see, on the surface, we have this kind of peeling. Is that not it? Peeling. So more or less this particular crustal material. So weathering rings, weathering rinse. And exfoliation has to do with this peeling of the rocks. And it has to do with the cooling and heating, contraction and expansion. We find this exfoliation. These pieces of evidence are all around Ghana. When we go around the Agona and Kwanta area, we find a lot of exfoliated granitoids, right? This is exfoliation. It's like onion peeling. We see how an onion peels, right? Layer by layer, onion peeling. So that is exfoliation weathering. Exfoliation. Then we could have another special type of chemical weathering called spheroidal weathering. Spheroidal, all right? So spheroidal weathering, in this case, we are also having rounded rocks, rounded. But the difference is that over here we had vertical cracks in the rock and horizontal crack in the rock, making the rock to be blocky. Vertical cracks and horizontal cracks, making the whole entire rock to be very blocky, a blocky mass. All right. So when we have this blocky mass, then when chemical weathering occurs, or when we have a lot of material water mixing with or reacting with carbon dioxide, we know it will form a weak carbonic acids. It will go through all the spaces, the cracks, and eat around the rock. When that happens, then we are going to have this spheroidal, like spheroids, right? Rounded spheroidal weathering. All right. So this is distinct from the traditional weathering, what's exfoliation weathering. That is because of the vertical joints and horizontal joints that is dividing the entire rock mass into blocks. All right. And this is also pretty common occurs in granite. Granite. All right. Granites. Because the edges will and the corners will undergo weathering at a faster rate compared to the flatter surfaces. So then we are going to have this type of spheroidal weathering. All right, so we see this big spheroidal weathering kind of stuff. So we should be able to identify them. All right. We also have a different or a special type of differentiation. All right, called differential weathering. Differential weathering. All right, differential weathering. How does differential weathering occur? We have a hard rock and a soft rock. Hard rock and soft rock. Hard rock. We know that when you expose them, move the hard rock and the soft rock to the same situation, the soft rock will undergo weathering faster than the hard rock. All right. And that is what we call differential weathering. When we have a series of rocks, so then we have one part of the one portion of the rock undergoing weathering faster than the other one. We call that differential weathering, because the harder rock is more resistant to weathering. It's more than the soft rock, because the soft rock is very susceptible to weathering. It's less resistant. So we call this differential weathering, different rates of weathering or breaking down the rock, differential weathering. So this is a typical example of differential weathering, right? The same area, the same geo-environmental conditions, but see this one. It's not very, these volcanic tuffs are still very strong, but look at this one, completely weathered. So this is the contact, right? And this shows differential weathering, differential weathering, because the two units are all volcanic tuffs, but this particular tuff is weaker than this type of tuff. So this is differential weathering. That's okay. This could also be two units, but under the same geo-environmental condition, one is weathering faster than the other one. So this is differential weathering. All right. So let's quickly look at the factors that influence weathering. So we know that the rock type and the structure will influence weathering, right? So different rocks, we mentioned, for instance, the limestone and then the sandstone, right? Joint networks, slope, climate, animals, and time. So all these factors are going to influence the rate of weathering, rock type and structure, slope, climate, animals, and time. So if we have steeper slopes, then it means that weathering rate is going to be faster, all right? Weathering rate is going to be faster when the slope is steeper than when we have, how do you call it? Horizontal, all right? When we have steeper slopes. Because we have a lot of action also acting, is that not it? So gravity itself is trying to push the material down. So with the little cracks, and when you add some water rain, then with the least possible action is going to attempt to move, all right? It's going to break down, all right? Then we could also talk about climate. We know different climatic conditions are going to have an influence of on weathering, all right? Then at the same time, we know animals could also burrow through and cause weathering, or even bigger animals could cause overgrazing, right? Overgrazing. And due to overgrazing, the surface of the rock or soil gets exposed, it easily breaks down into other minerals. All right. Then we could also talk about time. Time is a big factor in weathering, right? We need a lot of time. So the longer the duration, the easier it is for us to have weathering. So these are key factors that influence weathering. So now let's briefly wrap up today's session by talking about soil. So a soil is a natural body consisting of layers that are primarily composed of mineral mixed with some organic matter, right? So we know soils is the upper layer of the earth on which we grow our crops and all that. We equally use soil for building, right? Like sand. And we know that these materials or soil is going to differ from the appearance materials in their texture, structure, consistency, even color, chemical, biological, and other characteristics. All right. So soil forms a structure filled with pore spaces, and soil is a mixture. So we have the solids, then we know we have the void spaces. Is that not it? Or the pore spaces, the holes in the soil. And these holes can be occupied by water or air. So soil has three components: the solids, the hard parts, the solids, then the water in the soil, and then we could also have air in the soil, right? So the typical minerals you may find in or soil minerals are silica, quartz, like sand, right? Calcite, calcium carbonate, feldspar, then some biotites, which is a mineral, is a dark mineral, almost micas, right? Mica. So these are various minerals we could find in soils, all right? These are typical minerals we could find in soils, all right? And this is a typical soil profile. So we have the surface or the topsoil. We have, if you remember, the subsoil. We have the weathered rock, and then we have the bed or parent rock, right? So we could subdivide these zones. We have the topsoil, the subsoil, weathered rock, bed or parent rock. But then we could subdivide this into various horizons, all right? So we could talk about O horizon, the A horizon, E, the B horizon or layer, the K layer, and the C layer. So these are different layers. All right. So we can subdivide. So here we have surface accumulation of organic matter. All right. And this may or may not be present. Okay. All right. May or may not be present. In the A horizon, we see that we have a lot of humus. All right. Then we could also look at the E horizon, and this may only be present in some types of soils called acidic soils. Then we have the B horizon. So this is typically brown to red because it's enriched in clay minerals or iron. We know iron will give you a red color, brown to red coloration, right? Then we can have in some dry soils, we have only in dry soils actually, we have the K horizon. Then we can also have the unweathered rock, and then we could have finally the parent rock. In some places, these two can be combined in some texts as the unweathered material. All right. So briefly, we just have the topsoil, we have the subsoil, we have the weathered rock, and then we have the bed or parent rock. All right. So this is an idea as far as that one is concerned. All right. So are there any questions? In the absence of any other question, we'll be ending the session today. So I can pause here now, maybe for some 4 minutes. So take any questions that may be there. Right. So do we have any questions? Yes, can you hear me?
Yes, please, Doctor.
Yes, please.
All right. So are there any questions on all that we've covered? It's typically reading material. So yeah. For a good number of us, I know we have some people already have the foundation. So like I said earlier, for those of you who might not have covered these materials before in any form, you should be able to slow down the class as and when the need requires, so that all of us, not just me alone, we can take time to have a discussion on the parts that you don't understand. All right. That is what we are going to do. We know the introductory geology course is a lot of material, and we are trying to cover all that in less than 2 weeks. All right, in less than 2 weeks. So like I said, somewhere next week, we are going to give, I think, yeah, it's like the number has increased now, because initially we only had 3 students. So the new students, I don't know whether they have a background in geology or not. I think I can see a name here, Priscilla. Please, are you there?
Yes, please, I'm here.
Do you have a background in geology?
Yeah, a little.
So because you realize, because most people have the background in geology, I'm going at a pretty fast rate.
Oh, don't worry, I'll catch up.
All right. Yeah. So, and then senior Samuel.
No, please. I don't really have a background in geology, but I think I'm coping. I'm okay.
All right. So please feel free to reach out to me. All right. So you have the material too.
Yes, please. I do.
Is that okay? But feel free, even outside the class, feel free to reach out to me.
Okay, please. Yeah.
All right. So I know Asante has a background in geology. He did, I think, computer science and geology, right?
Yes, sir, that's right.
All right. So it means that you should be familiar with most of the material. It should be like a revision. Mike, you did civil engineering, right?
Yes, sir.
So you took some basic geology.
Yes, I did some basic geology
All right.
during my first year, so
All right.
I'm familiar with some of the concepts. The new ones I'm reading to get a broad understanding, but
okay.
There's a background in it.
All right. And then Richard.
Hello, Doc.
You have a background in geology?
No, civil background, but a little.
Yeah, I think in a civil program you do something on basic geology or something.
Yes, please.
Okay, all right. So you at least it's not totally new to most of you.
Yes.
All right. So like I'm saying, around I'm even thinking we could take next week Friday off completely. If we're able to finish the material on time, or yeah. If not, then we may. I was thinking about some presentations, but now the numbers increase. I may just give a take-home exam. All right. But I'll give a very short duration within which we will have to return the answers. Is that okay with us?
Yes, Doc. Yes, Doc.
Yeah. Then I think that should be sufficient. All right.
Yes, thank you.
So let's see. So the aim of the course, like I already said in the beginning, is just to provide you some, like the basic cover, the background that you lack in geology, because your project works for MSc or your thesis is going to be in geology, right? So just to understand, even when you are in civil engineering, most likely you are going to write something on the geology in your project work, geology of the study area and that kind of stuff. And we may even have to relate the geology to maybe the rock mechanics or the soil mechanics, right? For your project, whether foundation engineering, slope stability. And the rest of you, some of you may be going to maybe hydro, at least we should understand a little and explore. I don't know if somebody's going to exploration or geophysics. So I think that would be the end of today's session. I'll look through my schedule and then I'll provide the link for tomorrow, and then let's see how it goes. So thank you very much. Enjoy the rest of the day.
Yes, Doc. Can you please stay
Thank
on
you.
myself and you so that I can have an interaction with you?
Okay. All right, that's fine. So then the rest can exit. All right. Or you can you can call me directly on phone.
Okay, so I should pick your number from
the number is on the page. My number is on the page, so just call me directly. Yeah.
All right. I'll do that.
All right.
Thank you very much.
Welcome. Yeah.